Okay, I'd like to get started, please. I have one short announcement. It's occurred to us that there's a lot of expertise here that's not among the lecturers, and one of the things that we'd like to experiment with next week is to have the opportunity for one or two roundtable or caucus discussions on any subject that you think might be interesting. One suggestion that's been made already is visualization, in which either the people who know a lot about it or don't know as much about it as they would like just meet in a room and have an informal exchange of ideas. In order to decide what, if any, topics would be covered in these, I'd like to ask anybody who's interested in any such topic to send an email to Peter Teubin making the suggestions, and Peter will try to coordinate those and then maybe set one or two such sessions up in the afternoon during next week. I'd like to introduce the next lecturer, Frans Pretorius. Frans got his PhD in 2002 from University of British Columbia. The problem that he has worked on has been around for a very long time. I remember even back in the 1970s learning about relativists trying to carry out the numerical calculation of the collision and merger of two black holes in full general relativity. So this problem has been around for over 30 years. And every few years, as I went through my career, I'd hear somebody give a talk about it, and they'd say, oh, this is a very hard problem, and we've written down all the equations, and we can successfully evolve the black holes for 1/10 of an orbit, or maybe 2/10 of an orbit. But basically, we don't have any results. Then a few years ago, I was at a conference, and this young postdoc got up and showed a complete simulation of the collision and merger of two black holes lasting many, many orbits. And of course, I assumed that he was crazy. But then I noticed that I would start hearing talks from senior people in the field who all of a sudden were also able to evolve black holes all the way through the collision and merger. And they kept referencing the young postdoc I'd heard. Then I noticed that all of the quantitative results from these from this problem, things like the fraction of the black hole rest mass energy that came out in gravitational radiation, the recoil velocity of the black holes, all of a sudden started to be quoted to fractions of a percent error, and all of these papers kept on referencing this guy that I'd originally thought was crazy. So I eventually concluded that I was wrong, and the lectures will give you a chance to agree with that conclusion. Frans is now a faculty member in the Department of Physics and the Department of Mathematics and the program in Applied and Computational Mathematics at Princeton. So, Frans.
So thank you very much, Scott, for that very flattering introduction, and I'm glad that you don't think I'm crazy anymore. I'll hope to try to convince everyone else that what I'm saying is sensible and not quite crazy. So this is one of 4 lectures on computational methods for relativity. Here's an outline of the first lecture. So what I'll start with is just a very brief motivation of why we're interested in solving the classical field equations of general relativity. Then I will spend some time going over the basics of the mathematical structure of the field equations and highlighting a couple of the things which makes this a challenging problem. In particular, it's the general covariance of the field equations and certain other properties that, that from a mathematical point of view make it not so trivial to solve using analytic or numerical techniques. I'll also then highlight some of the properties of solutions that we're interested in particular binary compact object mergers. And the idea behind sort of describing these two aspects is that's going to tell us what kind of numerical methods we need to use to actually solve the field equations. And one thing that you'll see is, in the end, because we expect the solutions to be smooth, even though there are going to be a large range of dynamical length scales that need to be resolved, because we expect smooth solutions, we're not going to get shocks, we're not going to get turbulence, we're not going to get anything like that. the basic numerical methods are actually very, very simple. So the problems really boil down to, one, dealing with these mathematical issues in the field equations, and two, getting enough computer power to solve them in systems of relevance. Because at the end of the day, you get a relatively complicated system of coupled equations. You need terascale computing for these simulations, at least. So then after giving a little bit of an introduction to this, I'll go over some of the very basic techniques and give an overview again of some elementary finite difference methods, some of the concepts and principles, and I'm sure you're all familiar with that and you've seen it before. But the reason why I thought it would be useful to do that here is just to put a little bit of an emphasis on some of the things that we think are important or more important for numerical relativity. Then one of the projects that those of you that are interested in will be working on, the first project will be wave propagation on a black hole background. So sort of to introduce you a bit to the problem, I'll describe a little bit of about black hole physics, in particular what makes this slightly non-trivial, sort of more challenging than just wave propagation on a general background. Essentially, that's the event horizon of the space-time, adds a little bit of complication. And they'll describe how you solve hyperbolic PDEs. In particular, the one tool that I suggest you use is this RNPL, Rapid Numerical Prototyping Language. And if we have enough time, I'll sort of go over some of the this 1D wave equation example that's on the web page. And just show you how you go about using RNPL. It's a relatively simple language, and it's easier to sort of show by example. And for the case of then this wave propagation on a black hole background example that you'd be doing, it's much easier to take an existing template code and modify it from there. And even if it's a simple enough language that that's sort of the best way to learn it. So just to give you a bit of an outline for what I'm thinking about for the remaining 4 lectures. So this is again going to be a relatively broad overview to get you to the point where you can start working on this one project. For the next lecture, I want to spend a little bit of more time going into the details of the mathematical structure. And I think one of the most useful sort of decompositions to highlight the issues is the so-called ADM, or Orner-Wiedeser-Misner space plus time decomposition. So we'll go into that in quite a bit of detail, and then look at a spherically symmetric example using that formalism, and that will be a fully self-gravitating situation. So for this project, we're just going to take a fixed background and do a linear wave propagation on that. And then after we've introduced the ADM decomposition, we can look at a situation where we do solve the full field equations, even though it's in spherical symmetry. I mentioned that the basic numerical methods are very, very simple. Or you can use complicated methods, but you don't have to. You can just use very simple methods, such as basic finite differencing. Of course, but with a large range of length scales that you need to resolve, you need to be a little bit more sophisticated than just your unigrid type codes. And so one of the important methods is adaptive mesh refinement. So in the third lecture, I'd like to give an overview of Berger and Oliger style adaptive mesh refinement, how you solve elliptic and hyperbolic equations with this framework, sort of introduce sort of a software package that I use, AMRD, PAMR, adaptive mesh refinement driver, parallel adaptive mesh refinement, not very inventive acronyms, that I think will sort of aid in is something that's quite useful for solving these kinds of equations. Incidentally, if you like search on the web and look for packages that solve the full GR equations, you won't really find any like Athena or Zeus or the packages that Jim mentioned. And truly, the field is really not in a mature enough state where such ready-to-use packages are available. There are quite a few research groups that are involved in trying to solve the field equations for binary compact objects, but as Scott mentioned, I mean, most of the last 15, 20 years, when an intense effort was undertaken to try to solve the problem, has been trying to overcome the basic problems. And it's really only in the last few years that these codes are starting to work to the point where people can do physics and astrophysics with them. And it's going to be a few more years before all these the codes mature to the point where people are going to have ready-to-use packages that you can download. So at this stage, if you do want to sort of write code to solve GR equations, there's a little bit of coding that you're going to have to do yourself. You can sort of start by using basic packages. There are a few for example, that help with a mesh refinement or parallel distribution, or some like RNPL that help a little bit with a discretization. But at the end of the day, you're going to have to sort of glue these things together and probably do a bit of coding yourself. Okay, so let me just give a couple of slides on the motivation. So why do we want to solve the classical equations of general relativity, and in particular using numerical methods? I think the one reason is just for the sake of knowledge, trying to understand what is one of the fundamental forces of nature. So we think there are 4 fundamental forces. If you think of gravity as a force, it is definitely very relevant in our daily lives and in the universe, in many phenomena that we observe. So certainly trying to understand gravity is important. And so as of today, I think, you might, barring sort of your philosophical perspective of what dark energy or dark matter is, and if we say, okay, that's not a problem of gravity, I think today it is sort of safe to say that general relativity is really consistent with every experimental test and observation of something where, as the theory of gravity, to explain what we see. So since gravity is a fundamental force, general relativity seems to be the theory to describe it. We really want to understand it fully. And of course, what understanding means is finding solutions to the equations. We know what the equations are. They've been known for almost 100 years now. But to really understand what they imply, we want solutions in situations that are relevant. Now you might say, okay, after 100 years, well, haven't people found all of the interesting solutions? And the problem is that the field equations are nonlinear. There are many field equations, they're nonlinear and they couple. So analytic solutions are sort of very sparse, and they really only exist in sort of interesting analytic solutions in situations where there's some symmetry in the problem. And actually, luckily, some of the most interesting analytic solutions, the black hole solutions and the cosmological solutions, are very relevant. So, it's actually amazing that something like the Kerr solution exists. Yet, in more interesting situations where there's a lot of dynamics going on, there aren't any exact solutions. A lot of what we've learned about relativity, or what the community has learned in the last 20, 30 years, has come from so-called global methods. And they're extremely powerful. They've really given a tremendous insight into what general relativity is as a theory. And for example, by global methods, I mean like the singularity theorems of Penrose and Hawking that say if a trapped surface form, you're going to get a singularity generically. Or the no bifurcation theorem of Hawking, which says when 2 black holes merge, they have to form a single large black hole. So these theorems tell us a lot about the structure of what solutions that satisfy the equations have to obey, but they don't give you any details about the solutions. They're not solutions themselves. They just tell you what certain properties of the solutions have to satisfy. There have been very sophisticated perturbative techniques developed over the years also to study solutions, and they work very well in the weak field, slow motion regime. So objects which aren't strongly self-gravitating, where the local velocities are quite a bit less than the speed of light. But in situations, for example, in the final stages of the binary black hole mergers, all these approximations break down, and you really need numerical solutions. So to understand gravity, we want solutions. And there are regimes where we can't solve these solutions by analytic techniques. So that's, if you will, one of the motivations for studying numerical relativity. I think the other, perhaps more important motivation, or what's actually making this an interesting field of study today, is gravitational wave astronomy, or at least the promise of gravitational wave astronomy. And of course, it's from the sake of understanding and knowledge. You don't really need to justify exploring certain endeavors, but I mean, if a community is going to spend a lot of effort and taxpayers' money, etc., on some effort, there has to be a little bit of perhaps a stronger motivation, and that comes from gravitational wave astronomy. And as probably all of you know, there's a new generation of gravitational wave detectors, particular LIGO, GEO, and Virgo, and the planned space-based mission LISA. And various other ways in which people are trying to observe gravitational waves, pulsar timing, and looking at CMB polarization. But there's been, essentially, in the last couple of decades, there's been a real effort to try to build these detectors and measurement devices to try to look at the universe through gravitational waves, or also open up the gravitational wave spectrum to observers. The problem with especially this first generation of ground-based detectors is gravitational waves, even from the strongest sources, such as binary black hole mergers, and these are incredibly energetic events. And the luminosity, at merger time is perhaps, 5 orders of magnitude larger than the brightest supernova. Yet the corresponding distortion in space-time, which is what these gravitational wave detectors try to measure, is very weak by the time it gets to Earth. And so these detectors are not going to see gravitational waves directly. There are various ways in which they can sort of see that a gravitational wave has passed, but they won't know anything about it. So if the promise of these detectors to really actually observe the universe is to be realized, you need sophisticated data analysis. And the way that you do that is with so-called match filtering or something of that sort. And that's where you take a set of known template waveforms and you convolve it with the data and try to extract a signal. So for this program to work, in other words, for these detectors to really see something, we need to understand, particularly this first generation of detectors, we really need to understand what the field equations are predicting for sources that we think are out there. And again, one of the most promising sources are these compact object mergers, so binary black holes, black hole neutron stars, or binary neutron stars. In the final stages of the coalescence, to get these template waveforms to do gravitational wave astronomy, we need the numerical solutions. Okay, so let's sort of start now with a little bit of the nitty-gritty. So an overview of general relativity. Again, so I mentioned, gravity is one of the fundamental forces. But the sort of the geometric picture of general relativity is that gravity is not really a force. It's really saying that we live in this sort of curved space-time, that space-time has a non-trivial structure to it. And it's because of this non-trivial structure, we feel something that we call gravity. We feel this force of gravity. So the way that we describe, or one of the convenient ways of describing this non-trivial geometry is just through the metric tensor. So this is sort of the infinitesimal version of Pythagoras' theorem that just says that the distance squared between, or along some direction between two events in space-time is given by this sum. And so I'm using the Einstein summation convention where we sum over repeat indices. So in a 4-dimensional space-time, this is a 4x4 matrix, if you will, at each point in space-time. But it's a symmetric matrix, so there are 10 independent components to that. So if we know this for all space and time, this sort of characterizes the geometry that we live in, and therefore every gravitational phenomenon we should be able to understand by looking at the structure of the metric. So this is what we want to know. We want to know what the metric is in situations of interest. Incidentally, the thing that this differs from the usual Pythagoras theorem is that this metric is a Lorentzian signature. And within the convention that I like, the time-like direction comes in with a negative magnitude. So in particular, you can have distances that are positive, so the usual space-like distances, they can be negative, so for a time-like observer, causal signals, or null for photons. So if we say that, okay, gravity is really a non-trivial geometry, what general relativity tells us, or Einstein's equations tell us, what class of geometries are physically relevant given a particular distribution of matter in the space-time. So it's matter and energy that causes this non-trivial curvature in space-time. So these are the Einstein equations in the very simple tensor form. So this is the Einstein tensor is proportional to the stress energy tensor of any matter in the space-time. And this is probably the only slide where I'll use normal units. So in the rest of the things, I'm going to use so-called geometric units where g is equal to 1 and the speed of light is equal to 1. So how does this metric relate to the Einstein tensor? And you go from one to the other as follows. So first of all, taking the metric, you compute the so-called connection or Christoffel symbol. So here, again, Einstein summation convention, the comma here denotes ordinary differentiation. So this particular product, the first derivative of the metric, give us the connection. We then form this particular combination of the connection to make the Ricci tensor. So here you can see we're taking a derivative of the connection. So in other words, second derivatives of the metric. And then taking this combination, so the Ricci tensor minus half its trace, that's the Ricci scalar, and that gives us the Einstein tensor. So you can see if we substitute all of this into Einstein's equations on the previous page, effectively, if we want to solve for the metric, so in terms of the metric, what we get is, again, 10, because it's symmetric, so there are 10 independent components to the metric. We get 10 partial differential equations that depend on the 4 space-time coordinates. And incidentally, they coupled and so-called quasi-linear, in the sense that, if you just look at this a little bit, you can see that there are non-linearities in this equation. We have sort of a metric times its derivative. Here we have the connections multiplied, so there could be first derivative terms squareds. But it's so-called quasi-linear because the principal parts of the equation, so the second derivative terms, are only linear. So the non-linearities and the couplings reside in the lower order terms, so it's what's technically referred to as quasi-linear. So I guess from a sort of mathematical point of view, that's not as bad a nonlinearity as you might expect, but it still makes it non-trivial to find solutions using sort of analytic techniques. So in the end of the day, that's what numerical relativity is about, is solving the system of 10 coupled nonlinear partial differential equations. So the problems sort of arise immediately, because if you then say, okay, well, let's solve these equations, but the problem is, in that particular form, there's really no definite mathematical character to the equations. They're completely ill-determined, ill-posed. In other words, they're not hyperbolic, they're not elliptic, they're not parabolic. So if you try to solve them, discretize them, solve them, you can't get a solution. There's no unique, you won't be able to get a solution. And the reason stems from the general covariance of the theory, the fact that the coordinates that you use to describe a particular space-time is arbitrary. You can choose whatever coordinates you want, spherical, polar, Cartesian, etc. And a given space-time, which is a concrete geometry, can be described by an infinite family of different coordinates, in an infinite family of different coordinate systems. And every single one of those representations satisfies the same equations. So perhaps the simplest example, well, let's say we want to solve for Minkowski space, starting with the slice of Minkowski space at some time. You can imagine, okay, so we start with the metric, which is just diagonal minus 1, 1, 1, and we want to use the field equations to evolve it to the future. Well, the simplest example, you might think, okay, it's just going to be that forever, but you can introduce a coordinate transformation where weird things happen in the future, at least in the coordinates. And you can introduce any arbitrary coordinate transformations that you want to do that. So specifying as initial conditions, so thinking of this as initial boundary value problems, the Minkowski metric, that its first derivative is 0, you're still not going to get a unique solution. You first have to fix the character of the equations. So that's the first non-trivial step, is that in the form that implied on the previous slide, it's not a well-posed mathematical system of equations. And the first thing that you have to do is you have to fix the character of the equations. Now, traditionally, there's sort of been two main ways in which this has been done. The one that we're going to be focusing on here is the so-called 3+1 or space plus time decomposition. And that's where you sort of give you attach sort of some preferred character to certain coordinates. So 3 of the coordinates you define to be your space-like coordinates, and 1 you define to be your time coordinate. I'll just very briefly mention the other method, the so-called characteristic, where you define coordinates along characteristics, or the null cones of the space-time. But that hasn't really been as useful for some reasons I'll mention when I get there. So within the space plus time decomposition, so we're going to cover this in a lot more detail the next lecture, but just to give you some flavor, what typically happens is when you write the 10 field equations in that form, you split them up into a system of coupled elliptic and hyperbolic equations. So you get 4 elliptic equations, which are the so-called constraint equations. And if you look at the nature of them, they don't involve any second-time derivatives of the fields. So if you think of an initial boundary value problem, we have to specify the metric and its first-time derivative. They're constraints amongst those initial data problems. The remaining 6 equations are the so-called evolution equations, and they're sort of hyperbolic in character. However, in this decomposition, you still get 4 freely specified sort of gauge equations that you need to choose. So the second problem that comes up is in the sense that after you do this decomposition, you find that the equations are in some sense overdetermined. you specify your gauge, so you have 6 degrees of freedom remaining, sort of roughly, but you now have 10 equations for these 6 degrees of freedom. You've got the constraint and the evolution equations that they have to satisfy. So the way that this has been, there are several ways that you can go about trying to deal with this, and there are 2 traditional methods that have been used. One's a so-called free evolution. And in that case, you only solve the constraints at the initial time, and then evolve the rest of your metric with the evolution equations. The other method is so-called constrained evolution, which isn't, especially in generic 3-dimensional situations, that it really hasn't been explored much. But in that scenario, you try to solve the constraints at every single time step. And then instead of evolving using 6 of the hyperbolic equations, you use 2 of the hyperbolic equations to solve for the remaining degrees of freedom. So at the analytic level, so if you have a well-posed decomposition, and there are quite a lot of particular choices for the space plus time type decomposition. So in either case, whether you're doing a free or constrained evolution, you can show through using various mathematical identities. So for example, with the free evolution, if you solve the constraints at the initial time, evolving the space-time forward with a subset that just the evolution equations, you will preserve the constraints for all time. Sort of like the Maxwell equations with the div B constraint. So you can perhaps sort of think of it exactly in that form. So in some sense, it's not a problem. It's not really overdetermined, but there's more structure to the equations than is at first apparent just from a simple number counting. The problem comes in if you try to solve these equations numerically, in the sense that you cannot satisfy all 10 equations exactly at the numerical level. Like you can only satisfy all equations to within the truncation error of the scheme. And this has been particularly problematic for free evolution schemes. So you satisfy the constraints at the initial time. You then evolve the space-time forward with the evolution equations. The constraints aren't satisfied exactly. And what typically happens is you get exponentially growing modes. And these have really been one of the biggest sources of problems to why the numerical relativity has taken such a long time to actually get off its feet. And incidentally, so we've heard the discussions today by Jim of these constrained transport mechanisms. And again, you can think of, in some sense, you can think of these issues in the same way as the div B constraint in electromagnetism. But one thing is that the techniques that have been developed to deal with that in electromagnetism don't work in general relativity because of the nonlinearities in the field equations. And there have been some rather general studies of that that show that these techniques can't work because of the nonlinearities. And so you somehow have to have something else. You have to deal with those constraints in some other fashion. And so let's just mention, so after decades of looking for formalisms that don't possess these exponentially growing modes, and there literally have been, I would say, close to hundreds that have been investigated over the past 10 to 20 years. There are really only 2 free evolution schemes that are known that don't suffer from these exponential constraint growing modes in generic situations. And I'm putting generic in quotes here because there's no proof that these techniques will work in generic situations. It's just sort of empirically we tried them and they work. And that's the so-called BSSN, Baumgart, Shapiro, Shibata, Nakamura, and generalized harmonic. So as I say, in lecture 2, I'm going to describe this ADM decomposition, which isn't stable in general, but it's the basis for BSSN, and it also makes thinking about things in generalized harmonic clear. And you actually use this ADM decomposition for the initial value problem as well. So it's really sort of an essential starting ingredient for these 2 formalisms. And then in lecture 4, I'll sort of briefly go over and just show you the generalized harmonic and a little bit of the BSSM. Again, as I just mentioned, so the ADM formalism just by itself is only technically weakly hyperbolic, and it also does not preserve these constraints. It also has exponentially growing constraints for solutions that don't exactly satisfy the constraints in general, but in symmetry-reduced space-time. So it works very well in spherical symmetry or axisymmetry with certain gauge conditions. So in certain situations, those constrained growing modes don't arise. And the spherically symmetric example we'll look at will use the ADM formalism, and it's perfectly stable and well behaved in that example. Okay, so let me just a couple of words on this. One of the other approaches, that's sort of a null or characteristic decomposition. So again, this is now to try to get the equations in a form which is mathematically well posed for some initial boundary value problem. The other way that people have proposed is this null or characteristic decomposition. And when doing so, you choose one or two of the space-time coordinates to be null. So the distance along those coordinates is 0. In other words, photons sort of travel along those coordinates. At a first glance, this appears to almost like solve this problem of constraint violation immediately, because it turns out that you can formulate the problem in a way where there are no constraints. The problem with this, and why it really hasn't worked in general, is that these methods break down when you form caustics. And in the strong field regime, caustics are going to be everywhere. And there are some, in principle, ideas where you might be able to get around it when the light rays focus to a point. But so far, nothing has really been proposed that might work in generic situations. So the one place where they are finding some use in this field is so-called Kosher characteristic matching. So one of the important, as I mentioned, with binary black hole mergers, we want to understand what the gravitational waves are. When the black holes merge, there's no unambiguous way of sort of defining what a gravitational wave is close to the source in general relativity. So you have to be pretty far from the source to measure the gravitational waves and get some template for what LIGO might see. And with a Cauchy code, that's expensive to make the grid that large. And so with this Cauchy characteristic matching, what you do is in the interior, the strong field regime, you use a 3+1 decomposition. You get the waves to propagate out a certain distance, and then you attach it to a Cauchy code, a null code. And one of the null direction goes to null infinity. And so you propagate the waves out to infinity and sort of get the waveform that LIGO will see. So this kind of matching hasn't been completely worked out. It's got issues and problems, but this is still some area where people are doing some research in the field on. Okay, so that was a very brief overview of sort of the mathematical structure of the field equations. Now, to just talk a little bit about the kinds of solutions we might expect, and that will sort of guide us into what kind of numerical techniques we might want to use. And the thing, so you can always, in relativity, because of the covariance, you can choose things to be as bad as you want to be, but we're going to say we're not going to choose pathological coordinates. We're going to try and choose coordinates that are well adapted to the problem. And in that case, you can show that generically you're not going to get any kind of shocks or discontinuities in the field equations, and even if you couple it to matter, which does have shocks. And one way to sort of intuitively see this, if you again look at the field equations, remember we had the Einstein tensor is equal to the stress energy tensor of the space-time, but the Einstein tensor is sort of second derivatives of the metric. So we think we want to solve for the metric. In some sense, we have to integrate over the stress energy twice. And that's going to smooth out even a delta function in the matter. So in usual forms of matter that we expect out there, we don't even expect discontinuities as strong as delta functions. There might be steps, step functions, etc. So even if there's a matter that does form shocks or has complicated features in them, it's going to get smoothed out in the metric. So generically, we expect smooth solutions except at isolated points, and those are inside of black holes. So we know that generically from the singularity theorems that geometric singularities will always form inside of black holes, but they're going to be isolated and if cosmic censorship holds. So there's no proof to date that does hold. But this cosmic censorship conjecture says that all singularities that form in sort of realistic situations are going to be hidden behind event horizons. And because of the causal nature of event horizons, the nature of the singularity can propagate outside of the domain. And so these isolated singular points we can then deal with because of that property. We don't have to actually understand what the solution is doing in the approach to the singularity. We can sort of excise it from the domain. I should also mention there's also this so-called moving puncture method which deals with black hole singularities. I might mention a little bit about that in the fourth lecture, but for this first project, we'll look at black hole, a scalar wave propagation on a black hole, and use excision to get rid of that portion of the domain. And it's a very, very simple idea, as you'll see. Okay, so we expect the solutions to be smooth. So the other thing that we have to consider is what kind of range of dynamical, temporal, and spatial length scales do we have to worry about. And so there are several orders of magnitude that in typical situations you have to deal with. So for example, a compact object merger, there are about 3 orders of magnitude of spatial length scales that you have to resolve in a simulation. So the smallest is going to be the compact object, say the black hole, the neutron star. The second length scale is essentially going to be the orbital radius of the system. And that's where the strong field dynamics is going to happen. That's going to be producing the gravitational waves, where sort of all the interesting stuff happens. But as I mentioned before, in that strong field regime, there's really no unambiguous definition of what a gravitational wave is. You can measure properties of the solution there and just immediately infer what the gravitational waveform is. And so the practical thing to do is just go far enough away from the system where space-time is approximately flat, approximately Minkowski, and measure the waves as they reach that region. So you need this third length scale where the boundary of your domain has to be sufficiently in the far field regime where you can observe quantities of interest. So the smoothness property before says we don't really need complicated numerical schemes. We don't need these good enough methods. We don't need high-resolution shock capturing techniques. We can just get away with very simple numerical techniques. These length scales are not as bad as, for example, what Anatoly spoke about, going from the microphysics to the macrophysics. So in fact, we can, if we're clever about the numerics, and particularly use adaptive mesh refinement, we can resolve all of these length scales using contemporary cluster-based supercomputers. Okay, so just one comment on the right-hand side. I mean, for the most part, I'm not going to talk about matter at all. I'm just, except for the simplest kinds of matter. But in some sense, the complications of solving the field equations are really just with the left-hand side. In some sense, the right-hand side is not going to complicate things any further. And one way to see that is that sort of normal matter, quotes normal matter, is only going to couple to the local geometry. And from a mathematical point of view, the reason is the only way that the metric is going to enter on the right-hand side is just the actual value of the metric. Sort of the matter is essentially going to be propagating on a curved manifold, but there are no first derivatives, there are no second derivatives of the metric that couple to the matter. Which means from the formal mathematical theory, you're not changing the character of the equations at all. That's really just coming along for the ride. Sort of physically what that says is just sort of a manifestation of the equivalence principle. And that essentially on sufficiently small scales, things are locally Minkowski. So in some sense then, any matter that is local, so it doesn't couple to derivatives of the metric, should not pose any additional problems if you can actually solve the left-hand side. In particular, if you have a computational method that works in a special relativistic setting, so you might need to deal with very large, Lorentz factors, etc. But if you have a computational method that works for matter in those settings, it should be relatively straightforward, incorporating it into a full GR code. And of course, there's, the devil's always in the details, but at least I think. In general, you'll see that it should not be, there shouldn't be any additional complications that arise that aren't present in the individual methods to begin with. Okay, so we have smooth solutions, we have several orders of magnitude of length scales, and we have many equations with many terms, so we need lots of flops. So one thing is you really need parallel computing if you want to do general 3D types evolutions. And I'll talk about that a little bit in lectures 3 and 4. So lecture 3 will be adaptive mesh refinement, parallel computing. So if we look at the principal parts of the equation in a quotes good formalism such as BSSN or generalized harmonic, they're really just simple either Laplacian operators or D'Alembertian wave operators. And we expect smooth solutions. So the simplest numerical algorithm, just basic second-order finite differencing, is going to work. And what I'll show here in this example is something called Newton-Gauss-Seidel iteration to try to solve these equations. So the one thing that's perhaps not the simplest kind of numerical thing that you have to deal with is these are nonlinear coupled equations. And so you have to have a solution method that deals with that. But this Newton-Gauss-Seidel iteration is a very simple thing based on second-order finite differencing that works very well for the field equations. And incidentally, so depending on how time goes in the later lectures, I might describe a little bit on solving elliptic equations using multigrid. So this Newton-Gauss-Seidel iteration is a good way to solve hyperbolic equations that arise in GR, but it also is a very good smoother of the residual. And so the same method can form the backbone of a multigrid solver for elliptic equations. So this one basic method can take you a long way in general relativity. Right, so I'll say a little bit more about that when I describe it. It's also just mentioned that there are some other ways in which people solve the field equations. One very common way is to treat the time differencing in a slightly different fashion using sort of a Runge-Kutta or method of lines type integration. And there are some groups that also use pseudospectral methods. And again, from the smoothness property of the field equations, these methods can work very, very well and give you very, very good accuracy, though they are somewhat more complicated than the basic finite difference methods. And if you're not really interested in the very, very last decimal point of the answers, you can get away with finite difference. And especially for the initial generation of LIGO and like advanced LIGO, it's unlikely that you will need incredibly accurate waveforms. One can imagine that for LISA sources, we might need spectral accuracy. But I think LISA is probably 2020 at best. So we don't have to actually, I think, it's sufficient to first study the solutions using finite differences. Okay, I just sort of mentioned this before again. Given the length scales and one thing with these nonlinear equations as well is that we don't necessarily know where we're going to need resolution. So an adaptive mesh refinement technique is useful. In lecture 3, I'll describe this variant of Berger and Oliger style AMR. And again, it's very well adapted to this problem, particularly the binary black hole problem, because we don't expect volume filling small length scale features to develop. For example, turbulence or filaments of metric to fly or things like that don't happen. The non-trivial geometry is going to be confined into relatively simple volumes around the black holes or the neutron stars, and so we can get away with a relatively simple version of this Berger and Oliger AMR. So if we're solving coupled elliptic hyperbolics within this framework, it gets a little bit more complicated. I'm not sure if I'll have time to go into the details of that, but there are ways in which you can modify the Berger and Oliger algorithm to deal with these nonlinear elliptic equations as well. Okay, so let me just give you some of the very quickly go through some of the basics of finite differencing. So let's just denote a general system of differential equations by some differential operator acting on a solution vector with some right-hand side over there. So yeah, I'm not going to add indices, but think of this U as being our vector of unknowns, so the 10 metric elements, for example. And this L is the Einstein equations. So the way you discretize the system is first of all, you introduce some computational mesh where you evaluate the function. So I'm going to think of some characteristic mesh spacing H. So we discretize the functions on this mesh. I'm going to label it by U sub H. Same with any source functions or prescribed functions that exist on the mesh. And we're going to change the differential operators to difference operators. Right, so for example, you've seen this is nothing new to you. So these are some representations of difference operators. And incidentally, if you have sufficient smoothness in solutions, in particular if they're analytic, so in GR in general, you don't expect you don't need analyticity. But in some sense, these are exact relationships if you think of this as an infinite expansion in terms of H. So with the finite difference approximations, though, you throw away some of the higher order terms when you do this replacement. But the key thing, well, why I wanted to put up this slide is to remind you. So we've got a system of differential equations. So in that differential operator L, there are various combinations of partial derivative terms. We're going to replace them all with difference terms. So when we do a finite difference approximation of a differential system, we're changing a system of partial differential equations into a system of algebraic equations. And in this case, it's not going to be nonlinear algebraic equations, but we've essentially changed, say, for example, a set of 10 partial differential equations now into a system of n, where n is typically a large number of algebraic equations, because at each point in the mesh, there's going to be a set of, so for example, 10 of these algebraic equations. So if you have an n by n by n, say an n cubed system, you can have 10 n cubed algebraic equations that you want to solve. And so let's sort of represent this system of algebraic equations that we want to solve in this form. And so one step of a numerical algorithm involves taking essentially what are the known functions, which are the values of the fields at the past time levels, and trying to solve this system of algebraic equations for the unknown. So that's the values of all the fields at all the mesh points at the future time level. So some of the important concepts in finite difference solutions. So at some point, this is just a problem in algebra. But where all the numerics comes in is, in some sense, we're really not interested in the solution to this algebraic system. We really are interested in solutions that, to some sense, approximate the continuum partial differential equations. And so that's where all of these notions of truncation error, solution error, and convergence, etc., come in. So just to remind you, the solution error is defined. If we did know what the solution was, the solution error is the difference between the discrete solution and the continuum solution. So a similar concept is the truncation error, in the sense that if we know what the continuum solution is, and we apply the difference operator to that continuum solution, that gives us the truncation error. So the sort of approximation in the differential operator acting on the exact solution. We say that this discrete solution converges to the continuum solution if and only if, in the limit where the mesh spacing goes to 0, the difference approaches the continuum solution. Again, it's fairly obvious. Another, perhaps very similar statement is on the consistency of a finite difference approximation. And formally, this is defined to be an approximation is consistent if, in the limit where the mesh spacing goes to 0, the truncation error goes to 0. And you can see that that is a necessary condition for convergence. For a finite difference scheme, the other thing that's often that's an important number is the order of convergence, and that tells you how quickly this truncation error scales to 0. And so any finite difference scheme is going to have some polynomial. It's going to be some power of the mesh spacing that's going to determine how rapidly it scales to 0, and that's called the order of the finite difference scheme. Incidentally, spectral schemes have exponential convergence. So the truncation error goes to 0 exponentially, and that's why they have superior accuracy problems in situations where they do work. So an important concept is for example, the Newton-Gauss-Seidel iteration, or in general schemes that deal with nonlinear equations. Sometimes it might be impossible or too difficult or too expensive to solve that algebraic system exactly. And so you introduce some iterative method that just gets an approximate solution. And so if we take some approximate solution to the system of algebraic equations and we apply this differential operator to it, we get this quantity called the residual. And so in some iterative solution technique, what you want to do is you want to try to get this residual to be below the truncation error. You don't have to solve those equations exactly. You just have to drive the residual to below the truncation error. So formally, finite difference scheme is stable if some norm of the solution is bounded in time by an exponential, where this constant c there is independent of the mesh spacing. And so incidentally, so that the sort of, back in the last decade, when people were first trying to solve the field equations into generic situations, there was lots of debate about, well, perhaps you've just got an unstable code. Because you'd see these exponential growth in the code. But the thing that this sort of definition highlights is that stability allows exponential growth, and it must. I mean, exponential growth is a very natural phenomenon in nature. There are many things that do exhibit exponential growth. The thing that makes a finite difference scheme unstable is this fact that if it's an unstable scheme, you won't be able to find a constant that's independent of h. And sometimes you can think the reason of this is, in a sense, in finite different codes, typically the fastest growing modes, the unstable modes, the growth rate is proportional to the wave number of that mode, or sort of the inverse wavelength. And so as you go to finer and finer resolution, you're introducing larger and larger wave numbers, and so faster growing exponential modes. And so in the limit where h goes to 0, this constant c will go to infinity. That sort of denotes what an unstable code is. So exponential behavior is allowed, but not unbounded in that particular sense. And incidentally, this notion of stability still works if there's, say, a real singularity that forms in the solution, as long as you just exclude the singularity from the analysis. So in some region of time up to the singularity, this condition will still hold, even if the solution does formally diverge. Now, in some sense, all of these concepts that I've introduced are useless in any practical work, because in situations, like the field equations, we don't know what the analytic solution is. We can't compute truncation error. We can't compute solution error. In certain particular situations, we know what the exact solutions are. So yeah, certainly we can compare it in certain situations. But one thing that's those tests are perhaps not as useful in relativity as they are in things like MHD, like these shock tube tests, for example. Because what we've learned with the field equations over the years is that often these statements about the stable, like BSSN is stable or generalized harmonics is stable, depends very much on the coordinates that you choose, the gauge conditions. And we'll go into this in more detail the next lecture, but the coordinate conditions are not just saying, okay, spherical, polar versus Cartesian. These the coordinates are in a dynamical situation. You cannot differentiate, in some sense, the coordinate degrees of freedom from geometric degrees of freedom. So the coordinates are just as dynamical as the rest of the space-time. And as the interesting things happen, the coordinates are going to evolve. And so even if your code is stable in one particular exact solution, like the Schwarzschild solution, for instance, that doesn't mean in a dynamical situation it's going to remain stable as the coordinates evolve. So comparing a code or getting a code to work in a particular situation doesn't mean it's going to work in general. And in fact, I think that was one of the real difficulties in the last 15, 20 years trying to understand the problems in the field equations, because a tremendous amount of work went into trying to fix problems of various formalisms in specific symmetry-reduced situations. People were able to fix it, and none of them worked in the general situations because of the dynamics of the coordinates. So what is more practical, and this is, I think, really one of the key things that we're going to be using in this class of solutions, is based on the so-called assumption that a Richardson expansion exists for the solution. So we can't prove that in general this exists for any finite difference scheme, system of equations, boundary conditions, etc. But we are going to assume that at some discretization, that the numerical solution is equal to the exact solution plus something that's essentially a sort of a Taylor expansion in the mesh spacing. So P is the order of the scheme, so it's typically it's some expansion like this. These E1, E2, etc. are error functions, so they're functions of space and time, but the important thing is that they're not functions of the mesh spacing. So you can, for simple schemes, you can prove that this Richardson expansion exists. For more generic schemes, you can't. But we will sort of assume that this does exist. And if it does, then we can compute solution errors and truncation errors, essentially approximate solution errors and approximate truncation errors. And if we see convergence in that sense, that is in some sense a very non-trivial test that this Richardson expansion does exist. So the two most important things to take away from these few slides is this assumption of the Richardson expansion, and this allows us to do so-called convergence testing and error estimation. So if we assume that this expansion exists, well, first of all, again, we're not interested in U sub h. We're interested in U. We want to know what the continuum solution is. So how do we know that we're even close, we've got enough resolution that we're getting even close to the correct answer? Well, from this expansion, that will be the case if these quantities are small. So if relative to this E1, this h to the p is sufficiently small that this is much, much less than U, etc., and the higher terms are even less significant. So if we're in that regime where this expansion holds, then we can estimate what these error terms are by subtracting solutions at different resolutions. So the standard convergence test is you run your code with 3 different resolutions. I'm going to here say characteristic resolution h, 2h, and 4h. And then you combine, you form this particular quantity. So you subtract 2 adjacent resolutions, take a norm, and divide it by the higher ones. And if you are converging, if you're in this convergent regime, you'll get this constant here that's independent of the resolution. So for example, a second order scheme, this ratio will go to 4. So if you do see convergence, in some sense it's a very non-trivial test that this expansion actually does exist for the system of equations. And it's telling you that these higher order terms are not important. So if you see convergence, it's a good indication that your scheme is stable and that the solution that you're getting is a good approximation to the continuum equation. And if that's the case, so once you can demonstrate convergence, then you can use the 2 finest resolutions to estimate what this error term is. And so first of all, convergence to tell yourself that you actually are getting a good approximation to the continuum equation, and then you can exactly compute what this error function is by subtracting two resolutions. So you can present the numerical results with error bars, which is really important because at the end of the day, so sort of a philosophical comment, I mean, we often use the term simulation. We're doing computer simulations, but in some sense, in computational physics and computational astrophysics, we're not doing simulation. It's not like, in computer graphics where you try to do photorealistic rendering, or computer games where you try to simulate an environment. In some sense, we really are trying to solve a certain set of equations. And so it's not just important that we get solutions that sort of look good. I mean, if you have 2 black holes going around each other and they wave like things coming from them, that might be good enough for a simulation, but we really are trying to solve differential equations. And so it's really important that we can bound how accurate these approximations are to the real continuum equations that we're trying to solve. So in that sense, it's not a simulation of the equations, it's really an approximate solution that we're trying to get after. Okay, so after that, I presume that all these ideas and concepts you're familiar with. I just wanted to sort of re-emphasize, in particular, then this idea that we're assuming that there's a Richardson expansion and that convergence and error estimation are really sort of the bread and butter of getting believable and trustworthy results from the simulations. Okay, so now for this first problem. This first project, it's going to be looking at a scalar wave propagation on a Schwarzschild background. So I just want to give you, for some of you, a reminder of the important properties of black holes, and perhaps for some of you that haven't seen this before, just sort of the first introduction to black holes. So I think they certainly are one of the most important and interesting consequences of general relativity. And this is the usual way in which the metric for the Schwarzschild black hole is written. So if you want to think a black hole is a solution that represents a hypothetical point particle in general relativity. And interestingly, in Newtonian physics, you can think of hypothetical point particles. In some sense, in general relativity, there is no hypothetical point particle. They're only black holes, and they're not test particles. They're the real solutions if you had a central dense distribution of energy. So this is the Schwarzschild solution written in the usual Schwarzschild coordinates. M is the sort of asymptotic mass or gravitational mass of the solution. R is a radial coordinate. So this is spherically symmetric. There's no angular momentum. This is not the Kerr solution. So this is your time coordinate, the radial coordinate, and this is the geometry of a unit sphere labeled with angular coordinates theta and phi. So there are a couple of things that sort of perhaps would immediately pop out at you from this is that as you go to r equals 0, these two functions are going to become singular. And that really is a geometric singularity. That's not an artifact of the coordinates. That is the singularity that occurs inside the Schwarzschild black hole. And if you looked at sort of the consequences of this singularity, if you fall into the black hole, the tidal forces diverge as you approach this. So anything that falls into the black hole will eventually get ripped apart by this geometric singularity. The other problem that you might notice is when this particular combination of terms goes to 0, you also get a singularity in the metric. And that's at the event horizon. So when r is equal to 2m, this is 0, this is 1 over 0, it's infinity. But that is just a coordinate singularity. There's really no physical significance to that other than it marks the boundary of the black hole. So that really is the location of the event horizon of the black hole. So if you want to do some simulations with a black hole, this is really not a good coordinate system to use. And actually, for example, I mentioned the harm code this morning. There's a lot of interesting astrophysics that you can do by looking at matter on black hole backgrounds. For instance, accretion disk physics. Typical accretion disks are not going to be strongly self-gravitating. So essentially, they're not going to alter the geometry of the background. So looking at matter propagation on a black hole background is a very interesting problem. And so if you want to do something like that, you don't want to use coordinates that are singular at the horizon. For example, what is the accretion rate? If you have a coordinate system that's singular, it's going to be it's going to complicate things significantly trying to extract such information. So the first thing we want to do is change coordinates to a form where we don't have this coordinate singularity. And there are numerous ways of doing that, and there are many, at least for the Schwarzschild black hole, exact coordinate transformations that you can use. The one that we're going to use is so-called ingoing Eddington-Finkelstein coordinates. And I've written it here in terms of ADM variables, the so-called lapse and shift vector. I'm not going to explain that now, but we'll go over that more in the next lecture. But sort of in terms of these variables, this is what the metric looks like. And this is the particular value of the so-called lapse function, the shift vector. And this A quantity sort of rescales this radial coordinate. It's sort of the denotes proper distance in the radial direction. So this is still exactly the Schwarzschild solution, the same geometry, but now in this different coordinate system. And I think just from the form of these metric, you can see that there's nothing pathological at r equals 2m. But these are all finite. It's perfectly well behaved at r equals 2m. R equals 0 is still a problem. That's sort of the geometric singularity, but this is now a well-behaved coordinate system crossing the horizon. So we're going to look at a scalar wave propagation on this black hole background. And this is the general sort of the covariant wave operator, or the general covariant wave equation for a massless scalar. So these are covariant derivatives. So for those of you who've done tensor analysis before, the covariant derivative usually involves a connection, etc. But one interesting identity, or one very useful identity from differential geometry, is that this D'Alembert operator on a scalar can be written entirely in terms of ordinary derivatives in this form. So this is the scalar field. This is the inverse of the metric with the indices upstairs. This root minus GG is the determinant of the metric. So because the minus sign comes in here because we're using the Lorentz signature, so the determinant of the metric is going to be negative, so the square root is positive. So this is sort of a form of the wave equation that doesn't involve any connections. It's just ordinary differentiation. So we want to solve this equation with G given by the background for the Schwarzschild metric. We're going to restrict to the space-time is spherically symmetric, and just for simplicity, we're also going to look at spherically symmetric scalar fields. So the scalar field's only going to be a function of R and T. And then there's several ways of doing it. And one convenient way is sort of to reduce the equation to first order form. So essentially, we're introducing these conjugate variables, capital phi and pi, where capital phi is just the spatial gradient of a scalar field, and capital pi is essentially the time derivative, but it includes sort of this advection term given by the shift vector, and it's scaled by this function, a over alpha. And essentially, what motivates this definition for pi is really just this form. So I mean, there are, again, different choices that you can do, but this one sort of results in quite nice equations at the end of the day. So we're going to introduce these two conjugate variables. And in terms of those variables, the wave equation takes this form on a Schwarzschild background. And in a general system, but in particular in the Eddington-Finkelstein coordinates with the particular values of alpha A and beta that I had on the previous slide. So now we've gone from two variables to one variable. This is the wave equation. It gives us an evolution equation, a hyperbolic equation for pi. We can get a hyperbolic equation for this phi simply by using this definition. So essentially take the time derivative of this. You get a mixed derivative term here. Take the spatial derivative of this, commute the partial derivatives, and do a little bit of algebra, and you get the evolution equation for phi. So this is the wave equation. This is just the definition of these conjugate variables. So it's this particular system of equations that we want to solve to look at wave propagation on a black hole background. Now, so in general, solving the wave equation on some general background with a Lorentzian signature is, quotes, easy. I mean, these equations are just hyperbolic. You can just use very standard methods to solve them. The one complication that does arise with a black hole is the event horizon and the fact that it's sort of a one-way causal boundary to the propagation of signals. And in other words, once you're inside the event horizon, you can't get out. So any scalar field that enters the event horizon is trapped there. And the reason why that introduces a bit of a complication is that the characteristics of the wave equation tip over as you cross the event horizon. So you can show that in particular in Eddington-Finkelstein coordinates, for that system of wave equations, there are two directions in which characteristics of the equations propagate. So in the radial direction. And these are the speeds of propagation. So you can see if you're very far away from the black hole, so this m is a constant, that's just a mass. If r is very large, it's just going to go to plus or minus 1. So the usual characteristic propagation in Minkowski space. So as you approach the event horizon, when r goes to 2m, this one characteristic speed is going to go to 0. And that's essentially, those are the null generators of the horizon. So the event horizon is sort of ruled by these photons that are just sort of hovering there. And those are, that's those particular characteristics. The other one is going to be entirely negative. So you're going to have one characteristic that's just sitting there, the other one is negative. As you cross the event horizon, both speeds are going to be negative. So both ingoing and outgoing waves actually move towards smaller radial coordinates. So it's sort of like the picture of what's happening again. So you're very far away from the black hole. These are your two characteristics. You approach the event horizon, one characteristic's along the horizon, and you go to some point inside the boundary, and both of the characteristics are going inwards. So in the numerical code, we want to solve these equations on some finite domain. We don't want to include r equals 0. That's a geometric singularity. That will be problematic to deal with in any case. So we're going to solve the equations on in some range of r that's inside the event horizon to some distance outside. Now, why that's an issue is that the formal theory of differential equations, and this sort of it makes intuitive sense as well, is when you solve these equations, whether it's analytically or numerically, you can really only place boundary data on degrees of freedom that are propagating into the computational domain. All right. So, for example, here we have these two directions of propagation. So we have to place a boundary condition that constrains this incoming mode. However, inside the horizon, both of the modes are flowing out of our computational domain, and so we can't place boundary conditions there. Then it intuitively makes sense. You can imagine you've got a wave that's sort of propagating. Here, waves can propagate outwards, waves can propagate inwards. If we're going to have a stable numerical evolution, we have to say what those ingoing modes are. the wave equation on the inside cannot tell you what that is. So you have to place a boundary condition there for stability. In this case, all the modes are propagating in this direction. There's no freedom here in choosing what the value of the field here is. It's going to be completely determined by the nature of the field here. In other words, the wave equation is completely determining what the value of the field is at that location. And so you can't place a boundary condition there. If you tried, you'd get an inconsistency and you'd get an instability. So the complication with this one-way boundary in the domain is at this point you can't place boundary conditions. You have to solve the equations there. And at this place you have to place a boundary condition. And that's the idea behind excision. So in some sense, it's really trivial. It's just saying, okay, there's going to be some inner region inside the event horizon that you're not going to solve the equations for. And on that particular surface, here it's just a point. But in general, in 3D, it's going to be some 2 surface. You don't specify boundary conditions on that surface. You solve the equations there. And in finite difference language, what that means is you just, instead of using your usual center difference operators that sort of reference values on either side of the particular grid point, on those boundary points, you use a one-sided difference operator. So for example, if your I represents the point on the boundary, you'll just use points that are inside the computational domain. So you solve the equations, but replace center differences with sideway differences. Okay, one thing that's sort of trick that's been used quite a lot in numerical relativity and not so much in other fields is this idea of dissipation. And so often in various discretization methods, and in particular in these GR situations where you have these excision surfaces, you get these unwanted high-frequency solution components, often called noise, even though it's not noise. It really is a solution to the difference equations, but it's very high frequency and it's unphysical. And like you often find, for example, at refinement boundaries in an adaptive mesh refinement system, you might get this in various other locations. Now, for example, in a mesh refinement situation, at those things, at best, they're going to cause these unphysical reflections of waves, and at worst, these modes could be unstable. So in some situations, you can deal with these high-frequency modes by using difference operators, ones which have some dissipation in them. However, because in general, if you have an excision surface, any kind of operator you're going to use is going to introduce this high-frequency noise. And in mesh refinement situations, it's also going to be very difficult to find operators that don't produce this. And so one thing that's been very, very useful in numerical relativity is using the so-called Kreis-Oelerger dissipation to filter out those high-frequency modes. And essentially, all that this Kreis-Oelerger dissipation is sort of a high-pass filter. So you take some particular grid function and you convolve it with this filter, and essentially gives you what the high-frequency components of that solution are, and then you subtract it off your solution, so it acts as a low-pass filter. So this is the form of this Kreis-Oelerger term, and all it really is an undivided second-order accurate centered fourth derivative operator. So if you wanted a fourth derivative operator, you divide this by h to the fourth, but here you don't divide it by h to the fourth, and so essentially if you looked at the frequency response of this, it's really assigned to the fourth of the wave number of a particular mode. So incidentally, for a wave that's at the Nyquist limit of your grid, so an exact sawtooth, that's going to be pi by 2. And so it's going to essentially completely pass those modes through. And again, if you subtract it off then, it's going to completely filter out the very, very high frequency modes. So adding this to, in some sense, this is a very nice solution to the problem because you don't have to go fiddling out with trying to come up with very, very clever operators that avoid this issue. By adding this filter to the equation, you can suppress those high frequency solution modes. And the one comment is that this is not artificial viscosity in the sense that because this is an undivided difference operator, if you look at the level that it's affecting the equations, it's sub-truncation error. And in some sense, you can see that because of the response of this filter, it's not affecting any physical modes in the problem. It's only attacking the shortest length scale in the problem. So as you decrease the mesh spacing, you're decreasing the wavelengths that this mode targets. So in some sense, in the limit where the mesh spacing goes to 0, this filter converges away completely. It's sub-truncation error. And so the only sort of real cost of applying a filter like this is that typically, say you could find a solution scheme which was stable and didn't have these high frequency problems, is that with a Kreis-Hollergren filter you might need something like twice the resolution to get the same solution error at the end of the day. So it costs a little bit in that you need a little bit more resolution for the same error, but in some sense it's a really nice way to deal with all of these high frequency noise issues. Okay, so again, as I mentioned, there aren't really any sort of standalone GR packages, but there are various tools and libraries that sort of can help you write codes to solve these kinds of equations. And the one that we're going to use in this first project is RNPL, or Rapid Numerical Prototyping Language. It was written by Matt Choptwick, and a former PhD student of his in the early 90s. And it's a sort of a tool to aid in the construction of these kinds of hyperbolic partial differential equations. So the nice things about it is it gives you really sort of a simple and natural notation to define difference operators, and then to construct and then to write your partial differential equations in terms of these difference operators that you've defined. And the other nice thing is it takes care of a lot of the sort of the grunt work in writing a program. So you'll see that, so essentially, if I don't say anything else now, I've told you what this dissipation operator is. I've told you what the wave equation is that you have to solve. Basic finite differences. I bet all of you could go there, with Fortran or C, and write a little code that will solve a simple situation like a set of equations like this. Then you'll sort of get into the issue. Okay, you can run this code. It might spit out some numbers, but now you want to do visualization. So you have to save it in a format which a visualization program can use, or you want to have more input parameters, you want more initial conditions, etc. So as you start writing these programs, things get complicated by aspects which really have nothing to do with the equation that you're interested in solving, the wave equation. And so RNPL provides sort of infrastructure for doing file input outputting. It's got checkpointing facilities. It's got a relatively nice mechanism where you can read and run parameters. So in some sense, it's got all of this. It takes some of the grunt work out of writing simple programs to solve simple equations like that. At present, it implements this Newton-Gauss-Seidel relaxation algorithm, which is a really nice algorithm that works for a large class of nonlinear hyperbolic differential equations. So it provides sort of a standard method that works for a lot of difference equations. The disadvantages, so one thing is, even though it was designed for GR, let's get this is done. Okay, it was designed for GR, though it really doesn't have native support for excision. So this is actually not an issue with this 1D code. It's relatively simple. But if you want to do 2 and 3D things with RNPL, doing excision becomes very messy notation-wise. The thing is also, because it's only got the standard Newton-Gauss-Seidel relaxation, if you want to do something else like a Runcutter integration or whatever, it becomes pretty clumsy, and you have to sort of do that yourself. Also, I think there's people that sort of use RNPL. It's a really great tool, but you very quickly run into things. It would be great if it had this extra feature. So the thing is, doesn't have tremendous amount of features. It's sort of a research quality code, and not a commercial quality code. And one thing that I've often seen, some temptation is that people, when they do use it for some problem, they treat it like a black box. And that can be, in quotes, dangerous, because in some sense it's a really simple algorithm that it's implementing. If you don't understand that algorithm, you can sort of misinterpret the solution. I think that goes for any one of these packages. You really, if you don't really understand what's going on in the internal guts of the program, you can easily run into problems. So let's see, I've got about 10 minutes left. So just got a couple of slides. I think that the one might not have time to go go through the example in details, but I think that the one thing about sort of the internal guts of RNPL that's really important to know is this Newton-Gauss-Seidel iteration, and so what it uses to solve some system of nonlinear algebraic equations. So what you do with RNPL is you tell it you tell it what mesh you want to discretize the equations on. You define a set of difference operators, and you define a set of partial differential and boundary conditions in this form. Then what RNPL will do is at each grid point for each equation, it will construct a residual for that equation given some approximate solution. And then it will set up this Newton-Gauss-Seidel iteration to try and drive this residual to below some tolerance that you specify. Okay, what is Newton-Gauss-Seidel? In particular, one-step Newton-Gauss-Seidel iteration. So we've got, again, remember, we've got this system of, this large system of algebraic equations. They're nonlinear. We want to solve them given some known functions. In other words, the functions at the past time level. So Newton-Gauss-Seidel iteration is just simply applying these two steps iteratively until that residual is below some tolerance. So the first step is we linearize the equation. So that's the Newton part of it. So yeah, I'm not writing any subscripts noting all the grid points, but essentially, so we think of it, we've got the residual, and this label sub I is supposed to mean at every particular grid point for every equation that we have. So for example, this will be like 10 Einstein equations times the number of grid points. So we've got one equation for each grid point multiplied by the number of unknowns. That's going to depend on this approximate solution. And let's write the exact numerical solution as the current guess plus some correction that we want to solve for. So the Newton step is just doing one step of a Newton-Raphson type iteration. So this is exactly equal to the residual evaluated with this approximate solution multiplied by the Jacobian matrix. So the gradient of a given equation relative to a particular unknown multiplied by the correction plus higher order terms. So the first step is you linearize the equation, so you throw away the higher order terms. And then the Gauss-Seidel iteration is, so now we've got a system of linear equations that we want to solve for this correction. That could be very complicated. For example, with the Einstein equations, all the 10 equations will be coupled. In a multidimensional situation, depending on the different stencils you use, adjacent points are going to be coupled. So you'll at best have a banded matrix. So it might be complicated to solve that, or not expensive to solve that. So what the Gauss-Seidel iteration does is just approximates this Jacobian matrix with a diagonal. And technically the Gauss-Seidel also the one thing it uses is, so then you solve this linear equation for the correction, but only using the diagonal. And so you proceed through all the grid points, through all the equations. As soon as you've got it with the next correction, you replace the unknown with that correction. That's sort of the Gauss-Seidel part of the iteration. And then you just repeat this until the residual is below some tolerance. And this scheme works very well for hyperbolic equations if you solve with a good guess. So Newton iteration converges rapidly for nonlinear equations if you've got a good enough guess. And in hyperbolic equations, because things only propagate with a finite speed, if you use a solution at the previous time step, you will be very close to that final guess, and things can propagate. So typically this scheme, at first glance it might sound, if you have a very complicated coupled system of equations, it might take many iterations, but typically it rarely takes more than 10 iterations, even for something like the Einstein equations. And it's a relatively robust iteration scheme. So I think in 5 minutes it might be impractical for me to sort of demonstrate this example, but I think there's a link to the from the Twiki. There's a link to my web page, and this example sort of, the idea is to take this working code for a wave equation in flat space in RNPL, read through the code, look at let me just look through it. And again, as I said, RNPL is a relatively simple language, and I think the easiest way to learn it is just by looking at the example and then modifying it to what you want to do. And this is a project, and so this is something that I've taken from a previous summer school in Vancouver, and excuse me for not having sort of updated it for this one, but I think, I mean, that the guts of the project is the same. And I think the purpose of this school is, as I understand it, is, I mean, we're going to give you perhaps way much more work than what anyone could actually do in 2 weeks. But the idea is sort of like pick and choose aspects of the problem so that you can learn the most about it. So this is, quite a long exercise, and it's got a lot of, if you're not familiar with black holes and you want to learn a little bit more about black holes, it sort of goes through quite a bit of detail, explaining these equations, the characteristic structures. So if you want to sort of understand more about the mathematical formalism, I'd suggest sort of going through these problems and working it out, all of these things by hand. Though if you're familiar with black holes, or you just want to dive into the numerics, feel free to just sort of go to, just read through it. You don't have to do the problems, and just jump to the actual place where you start writing the code. And so the way to go about doing that is, so if you go to the web page, you will eventually get to this page. That handout that I showed you there is just over here. There are links up here where there is some documentation for RNPL, but again, it's a simple enough language that just looking at the code, I think it will tell you how to then modify it to modify this 1 + 1 flat space wave equation for this problem of a wave on a black hole background. In particular, this link sort of shows, again, it was instructions, but it sort of tells you how to take a 1 + 1D flat space wave equation and solve it with RNPL, and sort of introduces you also a little bit to this XVS visualization system, which you can use to visualize the results, do things like convergence testing, etc. I think as some of you have probably already noticed that try to install RNPL, that these instructions are sort of based on a particular flavor of Linux. And every flavor of Linux, there are a few little tweaks that you have to do to the makefile to get it to work. So I mean, if there are any problems with compiling it or installing it, just come and ask me. I find with every new version of Linux and every new laptop I get, there's always a little bit of a tweak. But I've now had a lot of experience. I think I can fix the problems pretty easily. And then I think from that point onward, it should be pretty straightforward to do this problem of a scalar wave on a black hole background. And perhaps the one interesting problem that you're asked to do when you have a working code is look at the scattering cross-section of some scalar pulse, a spherically symmetric scalar pulse falling onto a black hole. And perhaps the naive answer might be, well, black holes suck in everything, they're going to absorb everything, but that's not true. It's only really high frequency solutions that get absorbed. So the one thing you'd calculate is what the absorption cross-section is as a function of the input parameter of the scalar field pulse. Okay, so thank you.